trying to determine the remainder of this huge sum of numbers when we divide by 16. Now, of course, this is unmanageable by hand, but let's just take a look at what this looks like here. For I equals 1, you would have what, 3 to the 4th power? And then what's the next one? For I equals 2, you would have, for I equals to 2, you would have 5 to the, plus 5 to the 4th power, right? Okay, and then the very last one is what, 77, 140, 155 to the 4th power. So just that alone would be a pain in the ass to calculate by hand, just the last term. All right, so anyway, we need to figure out a way to do this more systematically. And again, these are odd numbers, as you notice. It's the sum of the first 77 odd numbers raised to the 4th power. Okay, so we want to find the remainder when you divide this sum by 16. Okay, now there's a result here that turns out to be huge. This lemma, which I'll prove for you, states that each of these summands is congruent to 1 mod 16. So you see, we'd basically be done once we prove this, because you just add up, this would add up to 77 modulo 16. Okay, then you just divide that by 16 and get your remainder, bam, be done. Okay, so, but this form here means the same thing as you can convert this congruence to just a straightforward equality. So that's what we're going to do. We're going to show this in our little proof. We're going to show that 2i plus 1 to the 4th is 1 plus some multiple of 16. Okay. So again, these are equivalent statements right here. 2i, I mean, this is absolutely equivalent to this. This is the modular arithmetic version of this. All right, now let's move along. Now, I didn't know of a better way to do this other than just do the binomial theorem, okay, the binomial expansion. And that's what I've done here. I think I've double-checked this and I haven't made any mistakes. But just an idea about where some of these terms come from. This would be, this term right here would be 4 choose 2. I'll just do one of them. Times I squared times 1 squared, you know, just for, right, 4 choose 2, and then we already, now, oops, sorry, that's wrong. This would be 2 to the I squared, sorry, this would be, let me erase that. Let me come back and get that straight, folks, for you guys. Okay, so this would be 4 choose 2, binomial coefficient. Now that's 4 times 3 divided by 2, which is 6. So the binomial coefficient is 6, but then it will be times 2i squared. And of course, I'll leave the 1 part off. It would be times 1 squared also. But this is equal to 6 times 4 I squared. Okay, so that matches up. And you do something similar for the rest of these terms, okay? Now, so I should have put an equal sign right here, shouldn't I? Yeah, notice you can rewrite this like this. 2i plus 1 quantity to the 4th minus 1 is equal to all of this. And you can rewrite this that way also. So we're going to show that this right-hand side has to be a multiple of 16. Okay, so let's do that. Now, the first thing that's pretty obvious is you can factor an 8 out. So right now we just have multiple of 8. Now notice there's 2 cases. Let me write above and below here because I crammed myself in here. What if I is even? Okay, if I is even, I even? Okay, if I is even, this part, this entire object right here will be even, right? Everything inside is going to be even, right? If I is even. So that would give us what we want. That would give us this form, right? The 2i plus 1 to the fourth is equal to 1 plus 16m, okay? When you bring this 1 back to the other side, right? Okay, now what about for I odd? For I odd, for I odd, okay, this is even, still all this stuff is even, but all these guys would be odd. But notice these two last terms would be odd if I is odd. But notice that an odd plus an odd is an even number, okay? So again, you get everything is even. And so you do get this form right here, 2i plus 1 raised to the fourth power equals 1 plus some multiple of m, right? Multiple of 16, excuse me, okay? Because again, we already had the 8 out here, and we've showed that it's even, this parenthetical quantity is even in the case I is even or I is odd, right? So kind of a slightly tedious argument. But anyway, we've proved this statement right here. We've proved the lemma right here. So that's a QED for proving the lemma. Now, so that means that we can replace the 2i plus 1 raised to the fourth power with 1, okay? Okay, and notice we have from equality to congruence right here. Now this is equal to 77. That's hard, isn't it? Okay. Now 77, let's see, what happens when you divide that by 16? Is this 4 times 16? 4 times 16 is 64. But then we have 13 left over, right? So that's going to be our answer, folks. Okay, 77 is equal to 4 times 16. And you can just think of 16 as being 0 mod 16, right? 16 is congruent to 0 mod 16, or you can just look at it like this explicitly. So the answer is 13 is what I got, folks. So that remainder would be 3. Let me just write it here. Okay, the remainder is equal to 3. You know, again, just I think this is pretty special in the sense that just the enormity of this, just computing this, and then think about trying to divide 16 into whatever that is by hand. You know, and that's just a massively almost undoable computation. You know, it's computable obviously with a machine, but for a human to try to undertake this calculation, and even if they correctly found the sum, divide by 16, can you imagine doing that by hand? Absolutely impossible. You know, but right here, the modular arithmetic, proving this, which was sort of cumbersome, not too bad, but it takes care of business. Modular arithmetic has a way of demystifying the magnitude of a bunch of large numbers. Okay, so anyway, I think I got all this right. 4 times 16 is 64, 64 and 13 is 77. Okay, that's all.